All right, so today we're going to look at linear equations, and we're going to start with some basic ones that you've seen since Algebra 1, and then we're going to build into some more challenging problems. So let's jump right in. Just some basic linear equations. This should be very familiar to you. When you're solving linear equations, remember linear meaning that the power on the x is to the first power, and we're just trying to isolate the x. So in this first one, we would subtract 3 from both sides and then divide by 2. Now, I know that some of you will want to be showing some steps in this, but by the time we get to college algebra, we kind of are flying through I don't need to show the minus 3 anymore. And so I'm going to just move through that without showing those kinds of steps. Some of you are probably good enough. You could have even subtracted the 3 and divided by the 2 all in one shot, and that's totally good with me. Okay, but let's look at something that's maybe a little bit more challenging than just that one, that just basic two-step equation. What if you got this weird fraction thing going on? Well, don't freak out. You're still just trying to isolate the x. Let's add 7 to the other side. And then we're going to undo that division by multiplying by the 3 on both sides, multiplying. All right, so then you get x equals 27. Next problem, we have the x in multiple places. That's okay. Let's just get the x's together on one side, the numbers together on the other side. I usually try to move my x the direction that will keep it positive. So in this case, it looks like I'm going to want to move the 3x to this side by subtracting it. So then I'm going to have an x minus 7 left over here. And then I'm going to add the 7 back over to the other side. So it looks like this. If you are like me, I'm going to OCD about having that x on the left side for some reason, but there's what you get. Some of you might be able to do 2 steps in one. Move the x's to the left, the numbers to the right, all in one shot. We got lucky with this one because the x ended up with a coefficient of 1, and we didn't have a division step at the end. All right, last basic problem like this, we're going to introduce some parentheses involved. You got the x's on both sides. You got a lot of stuff going on in this one. Let's start by getting rid of those parentheses. So I'm going to distribute the 3. And over here on this side, what you've got to recognize here is that this minus sign is subtracting this entire quantity. So that minus sign needs to distribute through the x, or through the parentheses. So you're going to have 7 minus x minus 5. Okay, this time it looks like I want to move my x's to the left side. So I'm going to add this x over to the left, and I'm going to have a 7x. And then at the same time, I'm going to go ahead and move this 12 over here on this side. Now I have a lot of numbers to combine. I have a 7, I have a 12, and I have a negative 5. Remember, this has already been moved to the other side. So I have 19 minus the 5, so 7x is 14. I'm getting really lucky here. These are all coming out as nice whole numbers. That will not always be the case. Divide both sides by 7, you get x equals 2. All right, so hopefully those are pretty basic for you. Let's move into something that kind of ties in what we were doing last chapter. In our last chapter, we worked with rationals, and we practiced simplifying and adding, subtracting, multiplying, dividing. Now we're going to introduce them as an equation. So now they equal some value, and so we'll have to do that same addition, subtraction, whatever it requires to try to get this solved this time. So using the strategies from last chapter, if I want to subtract these two rational expressions, then I'm going to need to get a common denominator. Now notice the 2 really isn't written as a fraction, but I could write it as 1. I could write it as over 1. And ultimately now, even though that's on the other side of the equation, I want to get a common denominator all the way through. So I've got a 4, a 3, and a 1. The common denominator would be 12. So let's look and see what we'd have to do to turn all of those into 12s. So this first fraction, I would need to multiply by 3. The second fraction, I would have to multiply by 4. Now be careful because you got this minus sign. I had a lot of people goof that up on the test. This minus sign means that's got to distribute to everything. So it's almost like I have a negative 4 here that I'm going to distribute through. And then the last one, I'm going to need to multiply by 12. Now, as I do this, I try to simplify up as I go. So I know I'm already going to have this common denominator of a 12 here. So I'm going to go ahead and merge the numerator, distribute. I'm going to have a 3x plus 6. And then remember, I'm basically going to be distributing a negative 4. So it's a minus 4x plus 4 equals 24 over 12. If you do it like this, ultimately what you would do, since you have this common denominator on both sides, couldn't we just take both sides of the equation times that common denominator? If I took this side times 12, it would cancel, and take this side times 12, it would cancel. So if you manage to get the common denominator all the way through, this will always happen. And you manage then to get rid of fractions. So it starts off as a rational, but you're working towards getting rid of that rational. In the numerator, I'm going to combine my like terms. I'm going to have a 3x with a negative 4x. So that's a negative 1x plus 10. So negative x plus 10, there's no fraction anymore, and it's going to equal that 24. Subtract the 10. Divide by negative 1. So x equals negative 14. All right, now do you remember in that last chapter where we were concerned about the domain always? Right here is why we are concerned about the domain. What if you had listed up here that your domain x cannot be negative 14? And then you went through all this work and you got x to be negative 14. All right, that's a problem. So this would end up being a no solution if that was the case. So we want to have that awareness of what your domain is. Now, that being said, look at all of your denominators. They're all just numbers. So there's no way you're going to ever magically have those end up being zeros. It's only when you have a variable in your denominator that you have to be concerned about that domain. So I'm okay. Now, we call this linear equations from rationals. So you're going to start with a rational, work on the common denominator so that it turns into a linear equation that we can go solve. All right, this one looks a little bit different. It's got these fractions in front of the x. So really, you got to think of this as an x over 1. When you say 1/2 x, that x is really up in the numerator. This x is up in the numerator. So on my next step, I'm going to bump that up. And then I'm looking at what's my common denominator with a 3, a 2, a 4, and a 3. Okay, again, it happens to be a 12. So let's work through this. This first fraction, I'm going to have to take times 4 to turn it into a 12. This fraction, I'm going to take it times a 6. This fraction times a 3. And the last fraction times a 4. Now, I'm going to combine this so that I just have a single fraction on both sides. I'm going to have a 12 for a denominator in both scenarios. Let's see what happens on the left side. This 4 is going to distribute through that quantity. And then this is just going to be remember this x is going to go up on top. So that's going to turn into a 6x there. So distributing, I have 8x plus 16 plus the 6x. All right, on the right side, again, this x is really supposed to be up on top. So I'm going to end up with a 3x, and then this is going to be a minus 28. 3x minus 28. Now I'm going to take both sides and take it times 12 so that those denominators will cancel out. And I have just this linear equation. I'll go ahead and combine the like terms as I go. No like terms here, but here I can combine the 8x and the 6x. So this becomes 14x plus 16. Over here, you get a 3x minus 28. I'm going to subtract the 3x to the left. And in that same step, I'm going to go ahead and subtract the 16 over here to the right. That ends up being negative 44. That's very convenient. Divide by 11. X is negative 4. Again, remember that the original denominators were all just numbers. These x's were actually up in the numerator, not in the denominator. So no worries on our domain. Now let's try one where we do have to have some concern about that domain. This x I'm going to put over 1. And right now, just looking at any of the denominators that have an x, which is really just this one right here, I would not want to let x equal 1. If x was 1, I'd end up with a 0 here. So off to the side, I'm going to put a little note, the domain, x cannot be 1. So I'll look out for that later on. Now let's go back to last chapter on getting common denominators with algebraic expressions. So this fraction is saying I got to have a 3. This one's saying I got to have an x minus 1. This is just a 1, so that doesn't really introduce anything new. So it looks like I've got to have a 3 and an x minus 1. So my common denominator is going to be a 3 with an x minus 1. So on this first fraction, I've got to multiply by x minus 1. Looks like I'm going to be doing FOIL on the top. The second one, I've got to multiply by a 3. Remember this minus sign, think of it like this to help you not miss out on that. Okay, over here on the right side of the equation, all I have is a 1. So I'm going to have the 3 with the x minus 1 that I'm going to be multiplying by. And then I'll have that common denominator of a 3 with an x minus 1. All right, let's start off by FOILing this first one. That's going to be a 3x squared. Outer is negative 1x. Inner negative 3x. Last is a plus 1. And then I'm going to also have this right here, this minus 6x. On the right side, I've got to take the 3 and distribute it, but I'm also taking the x. I would just merge these together and call it 3x and distribute it. So a 3x times an x is 3x squared, and then 3x times the 1 is a 3x. So I'm going to have a 3x squared minus 3x. Now, this is much messier, but the idea is still the same. I can take both sides times that common denominator. Change colors because it's starting to get a little messy here. So those are canceling out, and they're gone. On the left side, I'm going to clean up the numerator with any like terms. I'm going to have a 3x squared. I'm going to have a negative, let's see, what do I have? Negative 4, negative 10x and plus 1 equals 3x squared minus 3x. Now, remember, the idea is to end up with a linear equation from these rationals, and I actually end up with quadratic equations. But if you look hard enough, the first step would probably be to get these x squareds together, and look what's going to happen. When I subtract this over here, those 3x squareds are going to cancel out. Okay, so really, I'm going to go ahead and just cancel out the 3x squared on both sides. Now, because the only thing left on the right is the x term, I'm going to go ahead and add this 10x over here with it. Again, showing that step, but you don't really have to. So then I'm left with a 1 equals 7x, divide by 7. X is going to be equal to 1/7, which does not disagree with my domain up here. So I'm happy. I box it in. I'm done. All right, we're going to practice this one more time. This time, again, I'm going to do this 2 over 1. I conveniently have these two having the same denominator, so I obviously need an x minus 2. I just need to take this one times an x minus 2. So this one actually maybe will end up easier. Let's see what happens. Now, when we do this, we still have to determine what our domain is. So I would say in this case that I would not want x to equal 2, because that would create a denominator of 2. So put that off to the side. Remember, we'll check later. This first fraction will stay the same. This one ends up with a 2 plus, and now I'm going to distribute here. Thankfully, I have a positive sign, so I don't have to worry about that. So I'm going to add the 2x minus 4. Once you have condensed this to where you have each side with the same denominator, That's the point in which you multiply both sides by that common denominator so that it will cancel out. And then all we have left is x equals, oh, let's go ahead and combine like terms there, save myself a step. It's actually going to be a negative 2 plus 2x. I don't always love this, but I'm going to go ahead and subtract this because the only thing on the left side was the x. So that kind of is forcing me into moving the x's to the left. I end up with a negative x equals a negative 2. Divide both sides by negative 1, and you get x equals 2. Do you know why I'm not boxing it in? Because I said up here, oh gosh, look at that. I said, oh, big no-no there. It's x cannot be 2. That would be important. Okay, so x cannot be 2, and that is exactly what I got. So because of the domain, I would say this one is a no solution. So anticipate that happening sometimes. That's why that domain is important. All right, so let's talk through just a few scenarios here that can happen to us as we're solving linear equations. The most normal scenario is going to be this one right here. It is a conditionally true. It is true sometimes. If x is just the right value, then that is considered conditionally true. So in this scenario, I would subtract the 3. I would divide by the 2, and this equation is true as long as x is equal to 7. But sometimes you have weird situations going on. Like, I'm going to do this all out of order. The one on the right here is, they call it a contradiction. It's a no solution because when you solve this equation and you subtract the x on both sides, the x actually drops out entirely and you get 0 equal. 0 does not equal 8. So if you get a scenario where the variable cancels out like this and you get a false statement like this one, then we would write no solution. So these are kind of a special situation if the variable cancels out on you. Let's look at this over here on the left side, a different scenario. If I subtract the x on this one, again, the x's cancel, and I'm left with 3 equals, and 1 plus 2 is 3. Okay, now this one, the x is canceled, but what I got was a true statement. 3 does equal 3. If that happens to you, then we call this an identity. And what it means is that you could put absolutely anything you want in for x, and it will always work because both sides are identical, ultimately. That's why we call it an identity. All right, so all of these scenarios are going to happen on your homework, so be looking for different types of situations. The last thing that we're going to discuss here today with our, what we say linear equations, is something we call literal equations, which really means it's full of variables and not just a single variable, not just an x with a bunch of numbers in there. It's like almost all variables. And what we're doing is we're trying to rearrange it, doing all of those typical algebraic steps, but we're doing it with variables instead of numbers. So on this first one, I'm trying to solve this equation. This is an interest equation. We'll actually use it tomorrow. Interest equals PRT, principal times rate times time. I want to rearrange this equation and solve it for t. That would be handy if I was going to use this formula over and over and over. It's currently set up beautifully if I knew P, R, and T and I was solving for I. That's an I, not a 1. This would be great. But what if I had the scenario where I knew I, P, and R, and I was looking for T, and I was doing it over and over and over? Well, rather than having to do it and rearrange it every time, I would be better off to rearrange the formula once and then have it set up perfectly to solve for T over and over. So that's what we're doing on these problems. We're just trying to isolate a particular variable. Notice in this example that the P and the R and the T are all being multiplied. To undo multiplication, we're going to do division. I'm going to divide by P, and I'm also going to divide by R in the same step. Because those three are all just multiplied, So I'm going to divide by P and R here. These will cancel out. And again, I'm kind of OCD. I'm going to put my T that's isolated. I'm going to put it on the left side. And on the right side, I have I, if you want to make it look more like an I, not a 1, divided by the principal and the rate. And this way, I don't have to do algebra every time. Now, if I'm solving for T, I just plug in the numbers I know for those variables. Let's try a little bit harder one. Let's solve for P. This is definitely a trickier one. You might star this one. Take some good notes on this one. If I'm trying to isolate the P, what is problematic is I have the P in two different spots. So I first of all need to get them together on the same side. So I'm going to add P to, I'm going to move it over to the right. So I have A equals PRT plus P. Now I can't really add those two terms together because the first one is being multiplied by the R and the T. And order of operations says this would have to happen before I could ever add P to it. So the only way to isolate the P is to get it down to where there is only one P. And the trick that we have for that is to do a little bit of factoring. What I'm going to do is I'm going to factor out the GCF. The GCF happens to be P. And then what I have left is RT plus 1. You got to put a 1 as a placeholder. And by factoring that out, you've managed to have the P written just once. It is being multiplied by this quantity. So to isolate the P, I'm going to divide by that quantity on both sides. Then the quantities cancel. The P is by itself. I'm going to rewrite it, clean it up. P is equal to A divided by RT plus 1. So this would be way nicer if I was trying to figure out P than having to go through all the algebra up here every time. This is set up perfectly to solve for P. Okay, last one. This is actually looks like the area formula for a trapezoid, if you remember that from geometry. All right, we're going to try to solve it for capital B, which means one of the bases of the trapezoid. So these two B's represent different things. Sometimes we call it B1 and B2. Here we've used a capital and a lowercase. So it is very important as you write these formulas to stick with the capitalization that is given. Even if you're the kind of person that always writes in capital letters, you can't write this B in capital letter because that's different than this B. You would be able to do this different ways. Some people would like to distribute first. I think I would rather just get this mess over to the other side first. It's being multiplied right here. So I can divide by 1/2 h. So that's going to work great here. It's a little bit weird over here on the left side. You are taking A and you're dividing by 1/2. All right, we don't divide by fractions. We instead multiply by the reciprocal. So dividing by a 1/2 is the same as multiplying by a 2. So I would actually call that a 2a, but the h is still in your denominator. On the right side, I have my capital B plus my lowercase b. All right, last step, let's move that little b to the other side. And again, I'm going to rearrange, put capital B on the left, and I get 2a over h minus little b. Now, you can write this different ways. I am totally fine with it being written like this, but you might find maybe if you're doing like a multiple choice question or something, what you might see it written as, I'll go ahead and rearrange this. This is fine if you're just giving me an answer, but you might see that they have like worked on getting a common denominator, taken both sides times h, and then they might have written this as 2a minus bh all over the common denominator of h. And this would be another possible answer. So recognize that there might be more than one way to write these. All right, I'm going to call that quits. Hope this helped. Have a great day.